Hello everybody, I'm Marco D'Ambros and today we are going to see how to work with a capsule and interact with a capsule. So what we're going to see today is how to basically implement SDF or sign distance function in a segment. In terms of interaction, I use the collision because we already see some example. If you see some of my previous video, I see like how to collide with a maxi or bulge system. So we're going to use the same logic, but that is just like the way one way to interact. The goal here is to understand how to build a capsule. So if you can see now, I define a segment from point A, point B. These two locators are my 2 points. You can see slightly the line here, maybe not too much. So yeah, and when I go too close to some particular radius, I create that there is a collision, so I push the joints, the vertex away. Of course, this is a segment, so it can be defined by any 2 points. Can be vertices, joints in the bone, etc, 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 etc. The radius here, I make like a radius different from point A, point B, so you can define two different radius, and it's going to interact differently with it. Maybe we can see even better if I go down. So do you see? This is our capsule with the two different radius, and I can move it directly without any issue. So the way that this system works is pretty simple. Like I say, it's based on SDF. So what do we have and what we need? So we have a 2 point A and B, and these are gonna be our segment. So it's not gonna be like an infinite line like other example that I made. This is actually a segment. So it's start from A and end to B. We are going to have our target. Actually, let's write capital, our target. So what we want is to define the distance between this segment and this point. So in this case, this point here. Oops, this point here. We can call C for the collision as collision point. And we want to define this distance because this distance is going to define if he's inside or not our capsule. So I talk about capsule, but when I talk about the system, I always mention a segment. Why? So we're actually working with a segment, but if we add a radius to a segment, so this, for example, is a radius, here we go, we have a capsule. And like if you see the example then I made before, what we do, we can have different radius for point A, a point B. Maybe this is not a good color, so let's do pink. So we can have two different radius here, and the interpolation is kind of work like this. Here we go. So yeah, so that is our goal. So we want to understand this distance, and with the radius, one of the input that we have, we want to define if he's inside or not. This radius here, so this is going to be our radius, and if it's side or outside, we can define some particular rules of that. So how do we find this distance? Well, actually it's pretty simple. So the first things we want to define C. So we have two vector here, AB and AT. So we can define C. Actually, let's call this one T. The segment T is the projection of AT to AC. So AB. So we have AB dot product. Let's write these things here. So we are going to have our T equal AB dot product AT. And that is gonna be our first point. So of course, actually, to define AC, what we are going to do is going to get the normalized AB and multiply by the projection T. We can call it at the moment as C is equal to our T, our point A plus T. So now then we have C. That's it actually. So what we want to do is just define D, and D is gonna be our segment CT. And from now on, we can just do some work around it, etc., etc. One of the things we need to think about actually that I did not mention is our projection AC is gonna be clamp. So we never want to go below 0. Actually, sorry. not it, but actually our variable t is gonna be clump between it has like a limit in that region. It's going to be 0 to L to our length, so it's never going below this point or this point there. Okay, like let's do like with a proper example. I think it's much easier to show you how this things works more than just theory. So let's create like a two locator, actually three locators. So we have point A, point B, and a target. So we have point A, we're going to have point B, and we are going to have a target. So the first things that we want to create our Bifrost, and I like to work with the matrices just so I can give like word matrices, but we at the moment we just looking for a proper point. So even just the transfer actually it's fine. So let's do this one, let's do that one, and let's rename properly so it's not gonna be mess. Rename A, BB, and target, and the same is for this one, is gonna be A. I write in capital because it's a point, and we write point as with a capital. So now we have everything that we need to start. So let's bring our Bifrost node, and we can start to define to connect our transform. So let's get point A, go to the word matrix and connect to point A. Our point B is gonna be word matrix point B, and let's go. Our target is gonna be. I think I made a mistake on point B, so let's check again. Yeah, here we go. So now we should have, yeah, everything is connected. So word matrix and a different point. It's good. So now we have everything connected. The first things I want to do, I want to start to draw some segment, some line, just to have like a better visualization. And we can do with the construct. So actually, just get the construct strand. Let's create our terminal. Then is our node where we can draw stuff. So we can connect this one here. So just flat in this one, and we can connect point A point B. So now everything is connected. We can see here, there. So let's create another strand. This other strand is going to be, remember to flat in and connect with point A and our target. We're going to change this one in the future, but at the moment, just to have like a visual representation of everything we needed. Actually, it would be nice this one to create as an annotation. Well, let's try to do this. So create annotation. Here we go. And create annotation A. Cool. So we can have a nice annotation. We can even write in Bifrost, but why not? If we have Maya do this for us, let's use this one. Okay, cool. So now we have our annotation and everything. So the first things first, we want to create our two segment, like we say, the AB and AT. So let's use the node subtract, and let's subtract point B to point A, and this is gonna be our AB. And let's do the same on point A to T, and this is gonna be our node AT. So what we see now, AB and AT. So first things first, let's let's find our T or our projection. So that is gonna be dot product of AB. Oops. To AT. This is not actually correct. We need to normalize this vector, but I want to show you later. Let's see the wrong version, and we'll fix later. So now that we have this the product that is actually our T, but is actually just a vector. So we want to bring in a workspace, and to do so, we want to first of all we want to add we want to add on our point A. So we're going to here, we add a vector. This vector is going to be AB multiplied by our dot product by action. So let's do multiply. But to be correct, this one need to be normalized. Okay, so what we are, this is not what I want. Normalize. So what we just did is we normalize AB. So we're going to have a normalized vector here, and we multiply by t, so we know on this vector where is my c. This is why we normalize. So just we have like a unified vector, and just we can multiply r with a scalar. So now we have all these everything there. We can just create a sphere or any mesh. It's just to visualize. The radius one is a little bit too big now. So we can open the transform and set this one as position. So actually, so like I said, this is our point C. So now we can put that here. If you see that the sphere is here, and like you see, like it's interact with us, but very badly, and that is because our AB is not normalized. So let's bring the normalized vector there. So now that it's normalized, if you see, it works fine. So the other things we mentioned here is now we find T, so that actually is our T. So we want to clamp this T to and we want to clamp from 0 to 1, or actually 0 to our length. So our vector length. So let's create a clamp. 0 is fine. We want to, the max value will be length of our vector AB, our segment though, max. So now, if you can see, our point C is always be between these two. So we find this sort of like the closest point of our target inside this segment. We can move this one. Yeah, actually, let's remove this one. We can move this one. We can move this one, and everything works fine. So what are the things we need? So now we find our point C, and after we find our C, we need to find the distance, and the distance is very easy. We can find it do the vector CT. So we can just use the subtract. So this is gonna be our vector CT, and this is gonna be our. So what I'm doing now, actually, it's not something that I do that often, but sometimes I like it. It doesn't really, it's not needed. We don't need to do this kind of things, but sometimes I like to have like this vector just to bring this value around, so I don't need to connect from that all the time. But we can skip the things. It's just for me. So we can go T minus C. So this one is gonna to be our vector CT. We can even visualize that, so we can add this one to that one there. Actually, yes, it's missing like a one step, so that is why it's not correct. So now that we have our CT, what we need is let's find this point. So okay, so we have our sphere. So we have this vector, and this vector is the same things that we did for find the C. We need to add from C. So we want to from C add the vector CT normalized. So at the moment is going to have like length 1. And actually we can already add this one and see what's going on there. So if you see now, because it's normalized, the distance is going to be 1. If you see, it's actually already work as a capsule. Capsule of fixed radius 1, but it's still working. So what we have to do now, we want to, after the normalize, we want to multiply this one by a radius. And this is going to be our radius. There we go. Now it's 0 because is going to be 0 because by default this one is 0. So and if you see, we can change now this the radius and it's going to work fine. So now we have almost everything we need. So for example, so now we define the length of this object, and this length is going to be our where is it, sorry. So this is going to be our final point. So the length of this vector is actually our d. So we can define if it's inside or outside the radius, as now we can start to interact with. So for example, for the collision, the base rule is if the distance is measured at radius, we don't need to collide. If it's inside this radius, so less, we are going to collide, and this means push back our value. So how to do that is just like create a if condition. Condition is gonna be less. So if my length ct, so if my length is minus, then actually instead to use this one, let's go on input. This input is gonna be our radius, so let's do this one, rename radius. There we go. We don't need this anymore. So now it's back to 0 because when we created, oops, sorry, I made a mistake here. So let's recreate the input. I could actually change the type directly there, I guess. So let's create a value. This type here. There you go. Yes. So now we have this value here, radius. We can define, for example, 2. Okay. So we have our radius. So now our condition is if our ct is less than our radius, in that case we are going to have a collision. Otherwise we don't. So these are our output. This is gonna be our output here as well. Here you go. So if my length is minus the second one, we are going to have the collision here. Okay, and if it's not, we are going to have our t position. Vector 3, okay, here we go. Okay, so we got this one as an output, should be fine. Okay, so what we have now, like, so we don't have any collision at the moment. Let's just bring it to 0. We don't have any collision here, but when we go close it, if you see, we start to have the collision and is push away. And because this is a variable, we can even increase the radius, if you see, or decrease it, of course. And when I move my geometry here, my target here, and it's got outside the collision point, is continue to follow. There you go. So if you can see, when I go on the side, I have my capsule effect based on the radius, of course, etc., etc. So actually, that is the system. So let's see now how does it works to move it to transform deformation, like I show you in my video. So we have everything here. Then we have everything that we needed. So the first things we have to do is just move away this one, just select everything we have here in the middle and create a compound. This is gonna be our collision compound, capsule collision. So what we need is actually a mesh. So let's create a mesh. I create a plan just because it's the easy way to show you how these kind of things work, but any geometry is going to work. Let's remove this one. Okay, well, let's increase a little bit the details. We don't need a target anymore. So now we need to create just like the input output of our geometry. That is like almost on every deformer you do. You need to do the get the point position of our mesh, set the point position. That is like is practically the standard that you have to do all the time. So if you want to do any sort of deformer or similar, so you just select this one, select that one, connect, and just output aside. So now then is output aside. We don't need this one anymore because we need to connect first. So just bring this one inside and let's connect word mesh to our geometry input geometry. Okay, so as soon as we connected, our Bifrost node is going to draw the geometry, so we don't need this one. We don't need the visibility of our mesh anymore. So cool. So now then we have everything there. We just need one thing. So just copy and paste our system. Just connect the target. Actually, let's rename properly this one because I don't like this name. EA. EB. Okay. So as soon as we replace the target with an array, then our geometry point position, automatically this one is come back an array. We can set back this value. Here you go. And we already have the collision there. So the system that we designed first was already working, and on the system, etc. We just need to bring it inside a proper mesh. So like I say, I want to show you the radius still work. Everything is good. So in my example, I show you how to do like with two different radius interpolate with each other. So let's come back to our collision here. So we need to find our clamp value or T. So this one here. So that is where this is going to check in which point of our segment are every target. So we want to add here our change range. So we can define for every point where are the two different radius. So we want to start from 0, so this means point A, to our point B, then is our end. And we can define like radius, at the moment is going to be 0, 0. So let's add an input. And this input is going to be radius 1 or radius 2. So scale radius 1. B. Of course, you can use this one as a scale instead than a radius. It's up to you. So you can actually multiply this result to our radius instead to override like what I'm doing, but it's absolutely fine. So now you just need to connect here the collision and the result. Here we go. So at the moment you don't see anything because the value is going to be 0, 0. So let's go outside here and create an input for that. So we can just connect this one to our radius, for example, to our input. So now we have our input here, and we can just increase it. So this is the same, it works as the same day before, but we have two different radius, so we can increase radius of point A or point B. And everything works absolutely fine, as I showed you before. Awesome, that's it for today. I hope you enjoyed this video. Thank you very much to follow. Catch you next time. Marco.